Okay, so chapter 9 is about naming compounds and writing formulas. It's going to be a lot shorter unit than this covalent one was. There's a lot of stuff in this unit. And the last unit will be less than this one, be shorter. Okay, so why bother to do this? Why do chemists bother to come up with a systematic name that the name doesn't tell us anything about the compound usually? What does water tell you about the compound? If I told you there was a compound that was milk of magnesia, what would that tell you about the formula for that compound? And actually it doesn't. It doesn't have to. It's called milk of magnesia because it came from, because magnesia is a region in Greece. Okay? So names don't always, the common names don't always tell us anything. And there's way too many to memorize them. And they're different from one language to another. The name changes from one language to another. That would be a problem. And there's way too many to memorize. Millions and millions. So we're not going to be able to name all chemicals really here, but we'll be able to label the basic kinds of chemicals you're going to run into. Okay. So back to basics. A compound is made up of two or more elements. Or even more basic, in order to make a compound, you stick together atoms. And that's what I want the name of the compound to tell me. I want the name of the compound to tell me what kind of atoms there are and how many. The name should tell me how many and what kind of atoms there are. That from just the name, I can go straight to the formula. Isn't that a reasonable expectation of that for their name? We want to know how many and what kind. Two kinds of compounds. Heck, this was on the review sheet yesterday. There are molecular compounds. We have just spent the month of January learning about molecular compounds, things that are covalently bonded, things that are made up of molecules. We're going to recognize it because it's just nonmetals or nonmetals and hydrogen. That's why on the review sheet it asked why would CaO have a higher, which would have a higher boiling point, CaO or CS2. I was looking for you to recognize that one of those was ionic and one of those was molecular. CaO had a metal in it, so it was ionic. You can put hydrogen or not. So you're going to recognize it from the formula by the fact that it's just nonmetals or nonmetals and hydrogen. And that's what we've just spent the month of January studying. Go back and look at your homework. We only worked with hydrogen and the pieces on the right-hand side of the zigzag line. That's all we worked with for the past month. Everything was up there. And before the break, we studied ionic compounds. ionic, cations and anions. And anions are a negative ion, and cations are positive. In order to make a cation, you need a metal. In order to make an anion, you need a nonmetal. Metals are losers. Nonmetals are gainers, right? So the way you make a cation is by losing the electron. Where it goes is to make the anion. The metal loses the electron, the nonmetal picks it up. They do that to look like noble gases. And then once they look like noble gases, they surround each other. So it was different because we haven't been drawing them. We haven't been drawing compounds like this. A positive next to a negative, next to a positive, next to a negative, next to a positive, next to a negative. Alternating pattern. Versus, compare that to HOH. HOH is a molecule. That H is hooked to that oxygen all the time. This is not a molecule. You can't tell. This one lost an electron. Which negative took it? Can you tell? Is it sticking to the one that took it? Does it matter? You don't know if it is, and it doesn't matter if it is, right? So this is not a molecule. That was a formula unit. So in place of molecule, for ionic compound, we use formula unit because this right here is not held together the same as water. But it is the answer to the Bellwork question. In order to melt an ionic compound, I got to melt those charges that are right next to each other. In order to melt water, I've got to separate the partial charge on hydrogen on one molecule from the partial charge on oxygen on the other. That's a lot easier to do than to melt the full charges next to each other. Break those apart. Make sense? Okay, since there's two types of compounds, there's two naming formulas. We're going to do the hard one first, and we've already done it. Remember that the charge for each cation and anion, each cation in 1A is the group number. So the alkali metals make a 1 plus because they lose their valence electron. The alkaline earth metals make a 2 plus. And way over there at 3A, the metals there make a 3 plus. This is not new information. We use this a lot. It's about losing their valence electrons, right? Al has 3 dots, those come off. Ba has 2 dots, it's in group 2A, those 2 come off, so it's 2 plus. This is old stuff coming back. Okay, and in 5A, 6A, and 7A, it's the group number minus 8. So 5A, 5 minus 8 is negative 3, 3 minus, 2 minus, and 1 minus. Because to look like a noble gas, nitrogen has to gain 3 electrons. Oxygen has to gain 2 electrons. Fluorine has to gain 1 electron. So these lose electrons to look like noble gases before them. These gain electrons to look like noble gases after them. And that's why they get the charge they got. I'm going fast because this is review. All right? We've done this before. Okay. We could have used electron dots, but well, we're not going to do that. So, naming ions. We have named the group A ions before. the group A ions, the big tall columns, group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. The tall columns, the S's and the P's. And it's a cation, it's going to be a metal. And then you're followed by the word ion. I used this example before, but it's so clear. They tell you that you've got to drink milk because milk has calcium, and calcium makes for strong bones and teeth. You all heard that, right? You guys worked with calcium. You took a piece of calcium metal and stuck it into water, and it bubbled and fizzed and came out of the dish on you. Is that what's in milk? Does it bubble? Does milk bubble and fizz? No, because what's in milk is not calcium, the metal. It's calcium, the ion, after it's already reacted. So it's Ca2+, the calcium ion. So you don't need calcium for healthy bones and teeth. You need calcium ions, because calcium, the metal, blows up in your mouth. Okay. We did those before. But now we're going to deal with the ones that aren't in the columns we know. And that's the transition metals, the group Bs. And the real issue with the group Bs is not that we can't tell their charge by where they're at. It's not that we can't tell their charge by the number of valence electrons they have, because they all have 2. Well, most of them have 2, a couple have 1. But they have 2 because the s orbital is always higher in energy level than the d that follows it, so it's 4s than 3d. So the valence electrons is still the 4s. It's 2. So this would be 5s, 4d. 5 is still the bigger number. So all of them would have 2 valence electrons. But they don't all make 2+ charges. But that's not the reason why we don't do it. The reason why we don't do it is because they make more than 1. So, for example, cobalt. Cobalt sometimes loses 2 electrons, sometimes loses 3. Sometimes it makes a 2+, sometimes it makes a 3+. So they need to tell you in the name sometimes, somehow, they have to tell you which one it did. Did it lose 2 or did it lose 3? Okay? And the way they do that is they tell you the charge with Roman numerals in parentheses. So my example was cobalt. Sometimes it's a 2+, sometimes it's a 3+. If it's the 2+, if it's a 2+, I would call that the cobalt 2 ion. So you need to know your Roman numerals up to 8. Okay? That's I, II, III, IV, V, VI, VII, VIII. The only ones that are confusing are 4 and 6. And the way I remember it is in 4, the I is before the V. In 4, it's before. So, yeah, like the Super Bowl. Super Bowl does theirs in Roman numerals too. Okay. Now there's a few transition elements, silver, zinc, and cadmium, that only form one kind of atom, so they don't get Roman numerals. The Roman numerals are about the fact that you can have more than one. Not that we don't know, but the fact that you got to be specific about which one. When I was in high school, we had to memorize all the possibilities, and there was a different, we learned a different system, so you had to name the different ions differently based on their charges. So CO2 plus would be the cobaltous ion, whereas CO3 plus would be the cobaltic ion. Ugh. So Ag plus, Ag always forms a 1 plus, so we can call it just a silver ion. Zn2, zinc forms a 2 plus, so we call it the zinc ion. Zinc always makes a 2 plus. And cadmium behaves just like zinc. They're in the same column. And what all of them are doing is they're losing their valence electrons, their s electrons. Because silver is, its electron configuration is krypton, 5s1, 4d10. And when it loses an electron, it loses that one. Zinc is krypton, or sorry, it is argon. Argon. 4s2, 3d10. And when it makes the ion, those two come off. And cadmium is going to do the same thing as zinc does. Yeah, so all of them are just losing their s electrons. That's why they make them. You don't have to know how they make them, but that's why they make them. They lose their valence electrons. So let's name some ions. How hard can this be? Name this ion. You write sodium on your paper, and Mr. Green marks it wrong. Because sodium blows up in your mouth. Sodium ion. There's a difference between sodium metal and sodium ion. One of them really, really, really wants to get rid of its electron and will blow up to give it away. The other is happy where it's at. Doesn't react nearly as much. Because it already looks like a noble gas. It's okay. So Ca2 plus is, okay, calcium ion. Now, does calcium need Roman numerals? Well, where's that on the table? It's in group 2A. 2A is always 2 plus. If it's always the same charge, it doesn't need Roman numerals. If you could tell the charge by where it's at on the table, it doesn't need Roman numerals, except for silver, zinc, and cadmium. So that's the calcium ion. Aluminum. Al3 plus. So we got, basically, the key is, it's a metal, so I'm going to write its name. The only question I really got is, do I need Roman numerals for aluminum? What I find on the table. It's in group 3A. It's in an A group. And we said 3A always made a 3 plus charge, right? So if it always makes the 3 plus charge, then I don't have to tell you. If I say aluminum ion, everybody will know it's 3 plus. So there's no reason to say it. Somebody says aluminum ion, you can figure out it was 3 plus. Just by looking at where it's at on the table, right? So if it's easy to figure out, it doesn't show up in the name. If you couldn't figure it out, it has to be in the name. So Fe is iron. So I looked up on the table for two things. One, to figure out what its name is, it's iron. The second, to figure out where it's at. Can you tell its charge by where it's at? Nah. So since it can't tell its charge, I'm going to need Roman numerals. What Roman numeral should I have? What does it say right there? It says 3 plus. So that's the iron 3 ion. So when they write iron 3 ion, they're saying that that iron has a charge of 3. Why do they have to say iron 3 ion? Because of this. It's a transition metal, and the real reason is because there's also an Fe with the 2 plus. It can make the ones in here, they can make more than one charge, and you have to say which charge it is. Sometimes iron loses 3 electrons, sometimes it loses 2. So the iron 3 ion is when it lost 3 electrons. The iron 2 is when it lost 2 electrons. The Roman numeral is the charge. You can't tell iron's charge by where it's at on the table. That's a clue that it takes up more than one charge. Here's another way of thinking about it. I see like it's parentheses surrounding those transition metals. Right, those parentheses with some Roman numerals inside of them. It's almost a visual clue. Yeah. It does. What do you mean by it doesn't have a group? Everything has a group. It is a group number. The group number just ends in a B instead of an A. There's a number there. Officially they're numbered 1 through 20. But if you look at your periodic table, there's numbers on top of that Fe. It's on top of that Fe. It says 8B. That's what it says. It says 8B. Okay? So it's in a group, but it's not in one. It's not in group 1A, 2A, or 3A. 1A, 2A, or 3A. Okay. What about this? Pb2 plus. Where's Pb? It's right there. Its name is lead. Does lead need Roman numerals? What group is it in? 4A. What did we say about 4A? That's the correct response. We said nothing about 4A. I didn't mention 4A at all. I talked about 1A, 2A, 3A, 5A, 6A, and 7A. But I didn't mention 4. That's because 4 is not predictable. 4 needs Roman numerals. So that would be the lead 2 ion. Because sometimes lead loses 2 electrons, sometimes it loses 4. Because if it loses 2 electrons, it's a full D10. If it loses 4 electrons, it loses the P2 and the S2, it's a full D10 again. Okay. So the name for the Li1 plus ion? Well, Li's right here. Its name is lithium. Does it need Roman numerals? No. So it's called the lithium ion. So all you have to decide when you're naming metal ions is, does it get Roman numerals or not? You write the name of the metal, the word ion, and decide whether it gets Roman numerals. Pretty easy. Actually, that's the hard part, is remember to write those Roman numerals. That's what people do most often, is forget those. So what would you call Mg2 plus? Would you call it the magnesium, magnesium ion, magnesium 2 ion, manganese ion, or manganese 2 ion? Okay. And of course the answer is B. It's the magnesium ion. Okay, the bottom ones there are because Mn is manganese, Mg is magnesium. Different metals. Be careful with those two. People get them mixed up all the time. Manganese needs some Roman numerals. Magnesium doesn't. So what is the name of Ni3 plus? Is it nickel, nickel ion, nickel 3 ion, nickel 3 ion, or nickelodi ion? The answer is, it's C. It needs a Roman numeral, and the Roman numeral is a 3. Okay, they write it as a Roman numeral, not like this, because what's going to happen is people are going to think that this is how many, and it's not. Roman numerals don't tell you how many. They tell you charges. So let's go the other way. What's the formula for the potassium ion? What's the formula for the potassium ion? It's not a P. P is phosphorus. Potassium is K. So it's simple as K. Its charge, 1 plus or plus 1. Now, when I went to school, it was plus 1. But after that, they changed the official one to switch it around to emphasize that it's pieces. Plus 1 sounds like a math problem. That doesn't look like math, does it? Okay, so that by turning it around, it looks like a charge, not like math. 1 extra positive piece. Well, we shouldn't be. Well, magnesium ion should be pretty easy since we just saw it multiple choice a second ago. It's all a matter of finding where it's at. And actually, since it doesn't have Roman numerals, we know where to look. It's either going to be in 1A, 2A, or 3A. You don't have to search the whole table for this one. You know where it's going to be, one of those 3 columns. It's in 2A, so it's Mg2+. What about the copper 2 ion? Well, where do you look for copper? You look for copper somewhere in here because it's got Roman numerals. I find copper right here. Its symbol is Cu. I need to know its charge. I cannot tell its charge from here. That's why they wrote it there. Cu2+. That 2 is the charge. Try that one. So the hard part there is knowing what the Roman numeral means. Chromium is Cr, and that Vi is the 6. The I is after it. The I is before it's a 4, after it's a 6. Extra super hard? So we did this part, we did ionic compounds. We just didn't do this part. Okay, so that's what we're adding to what we did before. The other thing we did before with this was naming anions. So good thing is anions up here, none of those are in the places where the charges change. All the nonmetals are in groups 5A, 6A, or 7A except for carbon. So that means we will always know its charge. So I'm not going to need the Roman numerals. I just need to tell you it's negative and not positive. To tell you it's a negative ion instead of a positive ion, you change the ending to IDE. Again, we've done this before. In your toothpaste, you got F is fluorine. You don't have fluorine in your toothpaste. Fluorine will kill you. You have F with a 1 minus charge. I'd take off the ene and stick on ide and the word ion. And I put the word ion there so I know I'm done talking about it, that I'm talking about the fluoride ion. So if they're asking you to name ions, you get to write the word ion. Otherwise, you have it named an ion. Right with that? Really hard? There's no exceptions. Just do that. Try to get to one syllable, then "ide." So Cl minus. Cl is chlorine. So I take off the ene and stick on IDE. So that would give me the chloride ion. And 3 minus. N is nitrogen. Try to get to one syllable, so that would be nitride ion. You make a silly spelling mistake or not sure exactly where to cut off, I won't hold you accountable for it. But you generally try to get one syllable, then "ide." Br minus. Br is bromine, so I'm going to change that to bromide. O2 minus. O is oxygen. So one syllable, then "ide" would be oxide, the oxide ion. And Ga3 plus. Of course, the answer is gallium ion. If you put galliide, you forgot step 1. Ga, metal or non-metal? Ga, metal, left of the zigzag line. Metal, leave the name alone. Do you need Roman numerals? It's in group 3A. Group 3A is always 3 plus, doesn't need Roman numerals. So your first decision is not how do I name this, but which set of rules should I follow? Right? Do I name it like a positive piece or like a negative piece? See? And going the other way. What would the formula for the sulfide ion be? Okay, so sulfur is S. It's in group 6A, so I know its charge is 2 negative, right? So S2 negative. The phosphide ion. Name. P is phosphorus, so it's going to be a P. The question is which charge? Well, it's in group 5A, so that would, or another way of looking at it, it would take 1, 2, 3 electrons to make it look like a noble gas, so that makes it 3 negative. I usually just count. P3 negative. The strontium ion. So, first, look, it doesn't end in "ide." So it's a metal.
Teachers, sorry for the interruption. Attention staff and students, we are conducting a tardy sweep next period.
Why do you tell them?
Do not be tardy. Those who are tardy will receive a detention. Also, teachers, tomorrow starts our 2 days of block schedule. Please take a moment to remind your fourth period academy students about which months to attend based off of your class. Thank you. Have a great day.
Okay, have a great day. So, doesn't have "ide," so it's a metal. Doesn't have Roman numerals, so it's in group 1A, 2A, or 3A. It's in 2A, right? So, SR2 plus. The endings are important. I knew this was positive because it didn't end in "ide." So watch those endings. Make sense? So most of this should be familiar. We did it back when we studied ionic compounds, right? I thought about it. I just want you to get ready for the test. So just ready for the test notebook. I'll move the homework. Okay. But just keep in mind, since you have 2 days, but 2 days of class tomorrow, you have 2 days worth of homework. So that 9-1 will be due on Thursday along with something else. Does that make sense? So, yep, I do. Did you get the review sheet?
I think so.
Is that it? No, what color is it? What color did I make it? It was bright. I gotta get the phone. It's rolled. Mr. Green. Yes. Just trying to think. Oh, no, not a couple block schedule. I can't think of a specific date right now out past those 2 days that I can think of a special time. Doesn't matter, anytime.
Do I have to write absent on it?
The question is, do you want to come to honors or prep? Either one's, she can make her choice either way. The prep is first and second. Honors is